about how to encode information in sinusoidal signals using a process called modulation. We need to do this because we've assumed that all our signals up until this point have just been sinusoids. Sinusoids are handy because understanding how sinusoids move through our system and understanding the Fourier transform lets us analyze the behavior of arbitrary signals in linear systems. However, any individual sinusoid doesn't contain much information. If you know its value at one time, you know how it's going to behave at all times. So a transmitter sending a sinusoid over a link forever doesn't give the receiver any information about what's happening on the transmitter end of the link. We fix this by making small changes to the sinusoid that carry information. We have to build circuits to make those changes, and those circuits are called modulators. And we also have to make circuits to detect those changes on the receive side, and those are called demodulators. This equation shows a few features of a sinusoid that we can modulate, specifically the amplitude and the phase. Before we start talking about modulation itself, it's worth emphasizing that modulation is generally small changes to an underlying sinusoid, which is called a carrier. This is an important fact because it means that signals we produce by modulating a sinusoid are still pretty close to the original sinusoid. As a result, many of the assumptions we've made about RF systems, particularly ones that required a narrow bandwidth, still hold reasonably well for modulated signals. For instance, antennas are often narrowband, but a modulated signal can still make it through antennas as long as the fractional bandwidth of the modulating signal isn't too large. The carrier frequency is often fairly high, which has the advantage of making antennas that interface with it smaller. However, high frequencies make receiver design more challenging, which might be a decent tagline for this whole class. So, we modulate high-frequency signals to make it easier to launch our signal off of an antenna, then we demodulate those signals in order to build circuits that process the information more easily. Changing the coefficient in front of a sine wave is called amplitude modulation. This is the simplest form of modulation, and it's how AM radios work. You could argue that this type of modulation had an even earlier life in Morse code, which is a form of digital amplitude modulation. Instead of sending a continuous amplitude modulated signal, you send bits that are indicated by the presence or absence of a high-frequency signal. Every type of modulation comes in both analog and digital varieties, and the digital versions of amplitude modulation include on-off keying, or OOK, which is just turning the signal on and off to send data, and amplitude shift keying, or ASK, which is switching between two digital amplitude levels. Changing the phase of a sinusoid is called phase modulation or angle modulation. It's popular because phase modulation rejects amplitude noise gracefully, and because you spend more power on your information relative to your carrier in phase modulation as compared to amplitude modulation. But phase modulation tends to be harder to modulate and demodulate than amplitude. Frequency modulation is one extremely popular subset of phase modulation. In frequency modulation, we imagine the value of the phi of t modulating a sinusoid is the integral of a frequency signal f of t. So this has the effect of shifting our frequency back and forth rather than just jumping back and forth on a phase of one sinusoid. One other useful paradigm for analyzing phase modulation and sinusoid behavior in general is to define the argument of the sinusoid here as the total phase. You can then define an instantaneous frequency as the derivative of your total phase. This is useful when your frequency is moving around, as in the FM or PM communication schemes. This slide contains a picture of an amplitude-modulated wave and a circuit that implements amplitude modulation. Amplitude-modulated waves look about how you'd expect. The size of the wave gets bigger and smaller while the frequency stays the same. This picture represents digital amplitude modulation sending the bit pattern of 101, and this kind of amplitude modulation is often called amplitude shift keying. Zeros are indicated by one amplitude and ones by another. It's possible to encode more bits during each segment of time by having multiple amplitude levels to pick between. And it's also possible to modulate amplitude continuously instead of digitally. I've called out a feature of the amplitude-modulated waves called the modulation depth. This measures how dramatically the carrier is being changed by the modulation. If the amplitude of the carrier gets reduced to 0 when it's being modulated, then you'd say the modulation depth is 100%. As shown in the figure, it's about 50%. Modulation depth puts demands on the receive chain because small signals are susceptible to noise and large signals can cause distortion. So the modulation depth specifies the dynamic range of your receiver. Amplitude modulation is relatively easy to implement with circuits we already know about. We need to multiply a carrier signal by some other signal, and mixers already explicitly implement multiplication. So here I've shown a modulating signal getting mixed with a carrier on the LO port of this amplifier, of a mixer. The modulating signal is often referred to as the baseband signal, for reference. The output spectrum of the mixer is no surprise. Multiplication in the time domain is convolution in the frequency domain, so we get two copies of the modulating signal, one at each of the peaks of the carrier. Amplitude modulation is often said to be bandwidth inefficient because the signal that appears at each of the carrier peaks has twice the baseband bandwidth. If you consider only the positive spectrum, the baseband signal has a bandwidth of omega m, while the RF signal has a bandwidth of 2 omega m. Single sideband modulators can fix that issue. This slide contains a picture of a frequency modulated wave and a circuit that implements frequency modulation. Frequency modulated waves alternate between high and low frequencies depending on the modulating frequency, and I've tried to capture this in the graph I've drawn on this page. You need to be careful describing frequency modulation because there are actually a few different frequencies involved. The carrier frequency is one we're already acquainted with. It's the frequency of an underlying sinusoidal signal that our modulator is changing. The frequency deviation measures how much our frequency changes, so it's the maximum possible frequency minus the carrier frequency, or the minimum signal minus the carrier frequency if the deviation is asymmetric. Finally, the modulation frequency is how quickly we change between high and low frequencies. So it's 1 over this period, which is how quickly we shifted from a high frequency signal to a low frequency signal, how often we exercise our modulation. As on the last slide, I've chosen to show a digital frequency modulation here, and this type of digital frequency modulation is called frequency shift keying, or FSK. This in particular shows the pattern 101. In FSK, 1 bits are indicated by one frequency, while 0 bits are indicated by another. It's also possible to do continuous frequency modulation, and in fact that's quite common. It's what you hear on FM radio. You can implement frequency modulation with voltage-controlled oscillators. The DC voltage on the control terminal will set your carrier frequency, and variations from the DC voltage will set the modulation depth and the frequency. The output spectrum produced by the frequency modulation is not as straightforward as an amplitude-modulated spectrum, and just to scare you off, Bessel functions are frequently invoked when you're describing it. However, we mostly care about the total bandwidth of a signal when designing a transmitter or a receiver, and there's a simple expression for the total bandwidth of frequency modulation shown at the bottom of this slide. The bandwidth increases as we modulate our signal more dramatically, which is captured by the dimensionless modulation index. The modulation index is usually in the range of 1 to 5 for FM signals. This slide contains a picture of a phase-modulated wave and a circuit that implements phase modulation. Phase-modulated signals are often difficult to interpret, so I've included a particularly simple modulation called binary phase shift keying, or BPSK, which swaps between 0 degrees and 180 degrees of phase in the modulating signal. This is a type of digital phase modulation, and this wave represents the code 101 by flipping from 0 degrees of phase in the first period to 180 degrees of phase in the second period, and then back to 0 degrees in the third period. The sharp transitions when the phase flips by 180 degrees are particularly challenging for amplifiers and filters to render faithfully when this signal passes through a transmit or receive chain. So BPSK is a problematic encoding that people have thought a lot about. You can make phase-modulated signals in a few ways, but one that's within the scope of this class is called a phase interpolator. In a phase interpolator, cosine and sine signals are weighted by coefficients and added together, which results in a signal that has a phase somewhere between cosine and sine. The spectrum winds up looking similar to frequency modulation for The output spectrum of phase modulation winds up looking similar to frequency-modulated spectrums, and the total bandwidth varies with the amount of modulation, just like in the frequency-modulated case. And that's worth pointing out because in an amplitude-modulated case, the total bandwidth doesn't vary with the modulation depth. One last type of modulation is worth mentioning. We tend to think of modulation in terms of changes to amplitude and phase, but it's possible to express a modulated sinusoid as the weighted sum of a sine and a cosine wave, which are often called the in-phase and quadrature components of a signal. Accordingly, we can represent modulation using the coefficients of sine and cosine, which I've called I of t and q of t, instead of the amplitude and phase, a of t and phi of t. We can take this further and make an analytical representation of I and q, which looks like a complex coefficient that gets multiplied by a complex exponential. This is a useful representation because it's easy to imagine how to build an IQ modulator, and I've shown how to on the lower left of this slide. Note that the signal addition in this block diagram is probably accomplished using a power combiner, which is just the power splitters that we discussed earlier in this class plugged in backwards. It turns out they work in both directions. Most modern cell phones are built using IQ modulators that look like more complex versions of this architecture. Plotting the I and Q values that a modulation scheme considers as valid codes provides a convenient way to talk about different types of modulation. This representation of a modulation technique is called an IQ constellation. I've included two common constellations on this slide. QPSK is a quadrature phase shift keying, and it's a type of phase modulation where the phase is varied between 45, 135, 225, and 315 degrees. You can predict those angles from the constellation by looking at the angles on the IQ plane to each of the valid codes. Similarly, you can tell that this modulation scheme doesn't use any amplitude modulation because all the codes are the same distance from the origin. By way of contrast, QAM16 or QAM16, which is 16-code quadrature amplitude modulation, uses both amplitude and phase modulation to densely pack possible signal values into IQ space. So in summary, modulation is the process of modifying a sinusoid to add information to it. The things we modulate on our sinusoids are the amplitudes, which leads to amplitude modulation, or AM, phases, which leads to phase modulation, or PM, and frequencies, which leads to frequency modulation, or FM. There are digital versions of each of these modulation types that have different names, so amplitude shift keying, frequency shift keying, phase shift keying, and on-off keying. We modulate AM signals using mixers, we modulate FM signals using VCOs, and we modulate phase modulated signals using phase interpolators. IQ modulation represents the modulating behavior as weighted sine and cosine instead of a amplitude and a phase, but it conveys the same information. And IQ constellations are an easy graphical way to represent encodings.